Okay, so they shut down. Anyway, I have attached some of the material which we can still run the model, but I think we can obtain another resources for the Comcot data. Then wait me a moment. I hope that they just update the website. Okay, so I probably need to update the website. So yes, here you can find the EPUB global relief model. Probably one of the ways I can do it. Okay, so this is the thing that I worry about. The US government is closed, so this site will not be updated. But yeah, it's still to be used. I hope so. Okay, so we are here, right? So we can get the Comcot data. And then we can okay, so we need to enter some information. Large. For example, this is the target that we are going to download, and then we can download data. Okay, this is key. So you probably need to use the XGIS to transfer the TIFF data to SYZ data. So the SYZ data should be shown in this way. So we consider longitude and the latitude, and then this is the bathymetry. So here is one of the examples that shows the area near Taiwan. So if your study area is not near Taiwan, for example, Indian tsunami, and then you can probably extract the different area of interest, and then download data and then convert the TIFF data to the typical SYZ data before using the model. Okay, so this is the information that we need to set up for the bathymetry data. And the second one is the fault parameter. This is kind of the search engine that can provide you the event. So the earliest data I can provide is about 1976. For example, if our target is in 2011 to August, we can do it. Okay, and then we can search. All right, so in this sense that you can find that you set some criteria, they can produce, they can show you some typical information. So for example, here is the time for the date and the central time, and then the latitude and the longitude, and then the depth for the fault, and also the magnitude for the earthquake, and the fault plan, dislocation, and some slip angle. So all the information that you obtain here can be reflected to the Okada model. Okay. So the second item that I'm showing is form parameter. So right after you get those information in terms of the form parameter and the bathymetry, then we can go to the first one, the control parameter in the numerical model. Let's say the Comcot model. So right now is the time to turn on, to open the folder, to open the file folder I upload to the Moodle system. So let's open the first one, the example 01. And after open it, you can find the information that you can get from the model. So there are several information. So the first one, the .exe is kind of is scrollable file which can run the numerical model, and here is the user menu. So you can open it. So if you want to obtain some more detailed information, you can see this file, this document to know further knowledge based on this numerical model. Okay. Okay, so the Comcot.ctl is a control parameter file, so we can open it this way. Okay, so you can either open it in the Notepad or the Notes application for the application built in the Windows system. So either way you can try to open. Okay? So you guys follow me out? You actually can run this model. So there are several ways to run the model. The most simple one is double click. You can double click the model. Yeah, if you want to learn how to run the model, please see the projected monitor, right? Okay? You can double click the model, and then they will read some information on this. We can just run it, and then I just try to explain the detail to you guys. And the first step that they are doing is to read the bathymetry data, so it may take some time to find out that. And then after that, there is no warning information, not warning issue to you guys. So it seems that your setup is okay, and then you can run the model, and then you can press any key. Okay, and then the model is run now. But this is the stupid way that, so I did not recommend you guys to do it, because the command the exe file will shut down without any warning system you can see. So I recommend you open in the command window. So follow me up. Okay, so open the Windows start area and enter CMD command window. Okay. And then redirect it to the location for the folder that you saved in the computer. CD, and then is a direction. Okay? 基本上就换到这个资料夹啊 ，CD， 然后后面就是你看你这个资料夹存在哪个地方。Okay, so when you relocate it to the direction for the command window, and then you just enter Comcot. They will start to run the model. Okay? Okay, so if you run it smoothly, we can just let the model run, and then later on I will show you how to visualize the data. Okay, so let's go back to the parameter. So let's say the control file. Okay, let's start one by one line. Okay, so this is the general parameter for simulation, and you are not encouraged to modify any explanation in the left side. Okay, so the only way, the only location that you are going to modify is about beyond this dot line. Okay, so the first one is the job description, where you can enter any words that you want to show in the first line of the model, but you are not encouraged to enter the Chinese character. Okay, only English character. So for example, the description that I had here is the Taiwan area predicted tsunami number E1 for E1 is the number for the scenario. And then is the runtime, the total runtime. So, for example, for this simulation, I want to let the model to simulate 18,000 seconds. Okay, so 80,000 seconds is about 300 minutes, so which is equivalent to 5 hours. Clear? And then the following one is the time interval to set the data, which shows that this command determines the frequency that you want to set the data. So for example, here I showed you that I want to set data for every 30 seconds. Okay, so you can either choose the final one or coarse one. You can set the data for 1 minute, which is 60 seconds, and then you can do it for 10 seconds, for example. Okay? And then is the output data. So the output data in terms of the MESMA elevation, Z means the location for free service. And the second is the time series, and then the service report. So here I recommend you guys to set the MESMA elevation only. So in this case, you need to enter 0 in this zone. Okay. Okay, the next one is the start type. 0 is kind of a cold start, and 1 indicates a hot start. Cold start means you will start the simulation from initial condition, which means 0. Hot start means that you probably, due to some reason, you want to continue the simulation from a certain moment. But this is a kind of advanced simulation specification. So I encourage you guys to use the cold start for your project and for your exercise. And the next one is the time if you want to activate the hot start. So anyway, because we are not going to use the hot start, so we just do it in any way. And the next one is the specification for the minimum water depth offshore. This parameter indicates that if you want to do the inundation simulation, you probably enter 0. Otherwise, you can enter, for example, 1 meter, 2 meter, which means that you only simulate the location until this water depth. And beyond this, that will be treated as a so-called reflection. And the no inundation simulation will be done using the number which is larger than 0. Okay? And then the next one is the initial boundary condition. And we have several choices. The first one, 0, is the FNOT fault. Input the information based on this global CMT catalog. And then the second one is based on file. So we seldomly use the second one. And then the third one, number 2, WM is kind of a wave maker. We can either generate solitary wave or some any kind of a wave through a boundary. In that case, the model will serve just a typical shear water equation model. And then the fourth one is the Mesa-induced tsunami. So you can find the user menu to show that will guide you how to use this command to generate the tsunami Mesa-induced tsunami. And then the final one is kind of a couple one. A couple the fault induced tsunami and also the Mesa-induced tsunami. That will produce some severe situation for the tsunami event. And the specification for the boundary condition. We typically use the open boundary for the all 4 sides of the boundary. So you just keep 0 for this boundary condition. And this information is trying to input some information for the free surface and the flow velocity based on the actual measured data. So we seldom use this kind of input information. So you can just know that this model can have this function, but we typically doesn't use that case. Okay, so those are the general parameters for the simulation. And the next thing is now we are going to introduce is about the parameter for the fault model parameter. And in this model, we can provide several segments for the fault model. For example, we can input, for example, like 8 fault model simultaneously and try to generate a big earthquake, and then to see how the big earthquake will induce a tsunami. Okay, so we normally doesn't like to change the first rate. So we start from here. Okay? For example, focal depth. The focal depth means the location that generated a tsunami, generated earthquake, and then the length of the source area, wide of the source area. Some of the information you can find from here. So you can just do the reference. Okay, so for example, you can find the depth. The depth. So the depth sometimes is different. And and then the length of the source area, the width of the source area, so you can find okay, so some information probably cannot be founded, so you can just do the assumption. So here we know the dislocation for the fourth plane. Let's see if we can find it, right? Okay, no. Okay, so here is again the assumption. And the straight direction, yes, we have this straight direction, and the deep angle, deep angle, and then we have this information. Okay, so you can just do the input. And the origin of the computational domain for the layer 1, which reflect the boundary that you provide the pessimistic data. For example, if your pessimistic data cover the magnitude from 8 to 100, for example, so the original computational domain that you can start it can be within the range for this map that you provided. So that is the same story for the longitude. And then is the epicenter, latitude, and then longitude. So I think we have this, right? Oh yes, here is the epicenter for the latitude and the longitude. And the last one, the first, the file name for the deformation data, we are not going to use this because we are using the fourth option, 0, which is directly obtained from the Okada model, so that should be 0. So this command does not use it. And the data format for the option is SYZ, and also because we are not using it, so this command is remained here. And this, sorry. So the second source is that we are going to generate the tsunami by means of the wave maker. So here is the wave type. We can generate solitary wave. Input for type 2 for the given can be shown in this way. That can be provided as a time series. But we typically not use this. So I think if you want to do the simulation, just use the first one, that should be sufficient. And then is the instant direction for the wave. So for example, we have a foresight, right? So we can go back to check this one, for example. We have foresight regarding to the use of the typical Lambda setup over the dual setup in the Earth. So for the foresight, you can specify which side that you are going to generate the wave. For example, here is the top, here is the bottom, and here is the left, and here is the right. And then the number 5 is the uplift instant. So you probably need to give it an angle that can generate the wave. So to be simplified, if you want to generate a wave from the bottom, so just like the animation that you can see here, we produce a wave from the bottom. Here you just indicated the second option for the instant direction of the wave. And then we need to given the typical water depth and also the characteristic wave amplitude. So this is the water depth. So that based on the area that you're going to send the wave, and the amplitude is absolute. You can enter any number you like. Because we are doing a simulation, but it's just fine. You can be fine. You can enter, for example, 100 meters for a wave height. And also you can be more simple. So here, for example, I just enter 0.5 meter, which is about 50 cm. And this is a parameter for the submarine length and you can enter the information like this, but we are not going to introduce this one. So let's skip this. Okay, so the final one is the configuration for the grids. So that will be very important. So I think that the introduction or explanation for this input file is quite straightforward. So for example, they ask you if you want to run this layer, yes, so that should be 0. Coordinate system, spherical, okay, that should be 0. Governing equation, linear, that should be 0. But we can run the non-linear. So the typical classification for run the linear and the non-linear is that. Okay, let's use this one as an example. If we are running a pretty large area, the fraction, the non-linear effect is minor. So in that situation, for the outer run, we can just use the linear shallow water equation to run the model. But how about the second layer? The second layer still, we have a pretty deep water depth near the island or the Taiwan. So using the linear shallow water equation is sufficient. But you want to do the simulation for considering the bottom roughness or the information that the governing equation that we are going to use. And here is the grid size. And because we are running the model using the data for ETAP 1, so the resolution is going to be 1 arc minute. So that should be 1. And the time state that we typically enter 1 second, and the model can be adjusted based on the Coin number criteria. So it is also fine. Otherwise, if the time state that you are entering is too large, you will receive some warning information from the command window. And here is the bottom fraction. If you want to run the bottom fraction, yes, you can enter yes. Otherwise, just enter no. And enter the number for the maintenance roughness coefficient. So, for example, we can enter a typical number for the maintenance coefficient is about 0.017. And here's the output. What kind of data that you are going to generate? So, for example, if you enter 0, you can generate free surface elevation, horizontal velocity, and also the lateral velocity. And you can generate only free surface elevation, and this is the option that I'm going to choose in this simulation. And this is the boundary, so that depends on the bathymetry data, and also this boundary should be within the bathymetry data that you are providing. So, for example, the bathymetry data that I'm providing is starting from 110 and 30. So we enter this information, and then is up to. Okay, the minimum value is about 10, right? So here I enter 15 should be sufficient. Okay, so that's the start for the longitude and the latitude. And this is the file name of the bathymetry data. So for example, I use Taiwan01.syz. So this is the name for the bathymetry data. And the data format, and we use the ETAP data, so you just enter the ETAP data. The ETAP data and the SYZ data are in general the same. The only difference is the sign for the data. For example, I'm not really sure if it's correctly or not. So, for example, the ETAP data indicate the bathymetry as a positive value, but the SYZ data indicate the water depth as a minus value. So that's just only the differences between the minus sign and the plus sign. So in general, they give the same data formation. And here is the grid identification number. So don't modify any number appear in the last line of this input classification. Okay, so here is the do the structures is the same thing for the sub-level grid. For example, this is the 0 to grid. So we are going to run this layer in the same coordinate system, spherical coordinate system, and then the covering equation for the linear zero order equation. And then we are going to turn off the buffer fraction so the roughness coefficient doesn't work for this situation. And we also want to output to generate data for this equation. So we choose 1 for this classification. And this is important. The ratio for the parent layer to the current layer. The parent layer means the first layer that you are running the model. So for example, the parent layer that we are going to use here with the resolution of about 1 arc minutes for the DSN and D1. And the option that you are going to run here is to determine the ratio for the current layer to the parent layer. So for example, here I choose the ratio for 2. So which means that the resolution for the grid is only half of the arc minutes for the numerical grid resolution for this sub-layer system. And you can further narrow down the simulation area for S and Y, which directly reflected to the longitude and the latitude respectively. And then the final end of the water depth data, if you are going to use the same definition data, you just keep the same file name. But in some situation, if you are going to use some finer mesh data, although the resolution is different, you can put the different name as long as you have a file into the numerical model. And then the remaining setup going to be the same. Don't try to change it, otherwise you will get trouble in your numerical simulation. Okay, so for the layer 3, that remain typically the same. We are going to run this layer, coordinate system is a spherical one, and then we are going to run the notation. So we are using the nonlinear zero order equation in this situation. And then the bottom fraction is running. So we have the term for the fraction in the left-hand side of the equation. And the remaining roughness coefficient can be arbitrarily given. So based on the number of, the type of the fraction that you are going to input. So you can enter any value, but the value should be reasonable based on some scientific reports. And the output is again only the p-surface, and the ratio for the parent layer to the current layer. So please be aware of that. This ratio is to the parent layer, not the previous layer. Okay? So the ratio that we are going to say is 4. So which means that the grid size for the third layer is only a quarter for the arc minutes for the parent layer grid size. And then you can further narrow down the computational domain based on your purpose. And similarly, you can provide different water depth data if you have it. Otherwise, you can just use the same file data for the water depth. And then we are not going to choose it anymore for the remaining. And for the layer 4, and we are not going to run this layer, so we choose no, which is 1. And as long as you choose no, the following parameter which will not affect your simulation anymore. Okay, so that depends on your purpose. You can run the different layer up to 13 based on this setup for the record model. Okay? Okay, so you see, they are the model is going to be running, so it takes some time to finalize the simulation. So that's why I have also include some pre-run data that may reduce some time for the running the model. Then I can directly show you how to process with the data. Okay, so this is the the content of the data. So there are a lot of information. I think I have some, okay, here. I have included some MATLAB file for you guys, so you can plot those files using the code I have given to you. So let's open it one by one. For the MATLAB, you also need to redirect to the direction for the folder if you want to plot the figure. And then here is the data processing, and we can plot the free surface elevation map just like this. And this is going to plot the bathymetry data, so we can try to plot this one and okay, so we are going to open this. Okay, so this is kind of the function file. So how to use it? So we just enter the name of this function, and you should keep in mind that you also need to indicate the number of the ID. So for this simulation, we have run 3 layers. So you are able to plot the ID 01, 02, and 03. So, and the first one we are going to run the first. Okay, so here is the bathymetry for the first layer. So in this case, you can try to double check if the data for the bathymetry. Okay, so this is the first one, and we can also plot the second one. Okay, so the second one is pretty narrowed down to the area not near Taiwan, right? And the third one as well. Okay, so the third one is focus near the southern part of Taiwan. So for example, here is Fengdi. So sometimes I want to show you some example for the nuclear power plant near Fengdi. But because we have lots of holiday this semester, so probably I need to skip those information to you guys. So here is the narrowed down location for the southern part of Taiwan. Okay, so here is the bathymetry information. Then I would like to show you the input information based on your full model. So again, this is the initial condition. Okay, so this is the initial condition. So again, based on this, you can see, okay, this side is the positive side, and another side is the negative side for the earthquake generator tsunami using Okada model. So this is the initial profile for our numerical simulation. Okay? And then This one would be much more difficult. We want to plot the data processing. Okay, so here we need to enter some important parameter. So for example, the data that you are going to process is the starter step and the final step that you're going to plot. And the step is interval in the pre-ID. So you need to enter those 5 information. So here we can start from 0. Okay, let's start from 100. That should be fine. No. Okay, 300. Anyway, let's start from 0 at the beginning. And then we can end from 1,500. And the step interval is by because we output every plot by 30 seconds, so we probably need to enter 30 as the basic number, and then the pre-ID. So we just plot 01 at the beginning, and then enter. Okay, so now they will ask you several questions. So this one is trying to plot the color frame. Yes. And the input description of the plot, anything. So for example, here's ID 01, we just enter 01. And the input color scale, not be funny. So we can enter, for example, 2 meter. Using georeference image as a base map, that base determine depends on the purpose that you're going to do. So you can probably use the GIS map or Google Map as a background. So I'm not going to use it. Plot the velocity vector, no. Change the output range of the plotting, no. Extract the time series of recording. You can try to do it, but I'm not going to show you here. Obtain the arrival time control. Yes, you can do it, but I'm not going to do it. Also the invitation map. And the input is the time step size. So our time step for output is 30 seconds. And you can also account the effect of the title label by the linear assumption. So we just enter 0. Okay, I think that's all. Okay, here you can see some change in the plot. So they are going to show you the results. And at the same time, they also send the plot. So let's say export the video in the same folder. So here you can see your photo is generated lots of image based on your simulation. Okay, I think that is the all information I want to show you for the tutorial. So I think that next is the time for you guys try to practice. Okay? Okay. Sorry, one more thing I want to show you that.